Hello, Calculus 1 students. I was thinking about a few more problems here in section 5.1. We're learning how to do antiderivatives, integrals, indefinite integrals, and I like this problem. They want me to find the function, and what they gave me is the second derivative, and then they gave me a couple pieces of data. They're saying when x is 0, f prime is 3. When x is 1, f is 2. The function is, so they're giving me a couple pieces of information. Let's see what we can do. So how am I going to get from the second derivative to the function? Well, you know, the new idea is integrate. If I integrate this second derivative, I will be at the first derivative. Right? If you go from integrate antiderivative, the second derivative, you'll arrive at the first derivative. So let's try it. That's easy. We know our power rule. We know to add 1 to the power, that's x squared. Divide by 2. If I divide by 2, I think I get 3x squared. Oh yeah, plus c. Because we do it this indefinite integral, we get this answer. So that's my derivative. Now I'm going to pause here, and I think I can find that c. When they give me a piece of information like this, they're saying when x is 0, the derivative is 3. So when x is 0, the derivative is 3. Hang on, when x is 0, I'll plug that in. That'll be 0 plus c. The value of the derivative is a 3. When you plug in 0, guess what? C is 3. So now we know that first derivative is, here it was, but now we know the c. 3x squared plus 3. We found the c that met this requirement. All right, I'm trying to get to the function, so guess what? I play that game one more time. To get to the function now, you have to integrate the first derivative, do the antiderivative. So now I'm integrating this with respect to x. All right, here we go. This will be the function. That's what we're trying to find, the function. Power rule, x cubed, divide by 3 will cancel, so I'll get an x cubed. Integrate that, it'll be a 3x. And then I'll get another c. This is a different c. Sometimes you might call that one c1, and now this one's c2. I think I can keep track. This is a different c. And I'm done. I got the function, except it's this general, I got this general c. With this piece of information, I can plug this in and find c. So what this piece of information says is when x is 1, y is 2. This y value is 2. When x is a 1, I'm plugging in a 1 for x. This will help me find c. That's a 4. When I subtract it, that'll be a negative 2. So this c is negative 2. So we have our answer. Our function is x cubed plus 3x minus 2. That's the function that has that second derivative, and it meets those requirements. Sometimes we call those initial values, or sometimes they refer to this as we solved a differential equation. This was a differential equation we solved. It took a couple of integrals. So there's a couple ways to word this problem. But there we go. Now I'm going to elaborate on this. I'm going to get rid of it. So I'm going to erase it. You might want to hit pause and copy it or whatever you want to do. But I'm erasing it. And this idea extends into this now. I want to talk about what we used to call falling objects. And falling objects, they used to have this equation. 1/2 g, negative 1/2 g t squared plus v naught t plus s naught. In most of our problems, we were on Earth, and when we're on Earth and we were dealing with feet per second, our gravity was 32. So maybe you remember that gravity was 32 times, that was a 16, negative 16. T squared plus v naught t plus s naught. And you could take the derivative of this and get a velocity equation. Remember, we called this the velocity. The derivative of the position equation is the velocity equation. And that would be a negative gt plus v naught. And you could take the second derivative, and that'll give you acceleration. Acceleration, which is just gravity. There's gravity. Acceleration is your gravity. So, but so this is old stuff, but we revisit these problems, these falling object problems. And the reason we revisit them is maybe now you don't have to memorize this equation. I mean, the idea here is is we start with this g, we derive this equation. Now I might just do it very informally here. If I was to integrate a g with respect to t, hang on. So I'm starting with the second derivative, sort of like the previous problem, and I'm going to work my way back up. So I'm integrating this g with respect to t. So g's a constant, the variable's t, and the answer is gt plus some c. And this is the velocity equation. There it is. That's the velocity equation. But guess what the c is? The c is that initial velocity. All right, let's integrate again to get the position of equation. So when we integrate this, it's t squared over 2. I'll be darned. T squared over 2, negative 1/2 gt squared. Integrate this number with respect to t, and you get v naught t plus some c. And that turns out the c for the position equation is the initial position, s naught. So that's cool, and we revisit these falling object problems. We also do some stuff with acceleration that's not a falling object. So when we are a falling object, your acceleration is gravity, and maybe it's on the moon, maybe it's on Mars, maybe it's on Earth. So maybe it's on some unknown planet where we don't know g. But also, I can be a car accelerating from a red light, could be my acceleration from a green light when the light turns green. Or I could be a guy running away from a bear, and I could be accelerating to run away from a bear. So then your acceleration is in here. We could call it A, and it's almost, I guess it's these same equations, but it's not g, it's not gravity, it's just some acceleration A. So let's do one here. So let's say this happens. There's a car, there's some in the book like this. There's a car sitting at a red light. It's stopped at a red light. And when the light turns green, it begins to accelerate. And it accelerates at 10 feet per second per second. Now, at the same moment, there's a truck that came cruising through there, and it came and it cruised. What it did was it wasn't stopped. It was moving, and it timed the red light perfect. So when it was just moving though at a constant velocity, of 30 feet per second. So the question is, the car stopped. The truck hit the red light, timed the red light perfect. It went cruising past. Now the car accelerates at 10 feet per second per second. How long will it take the car to catch up to the truck? So for the car to, the truck's way ahead now, and the car's catching up. The car is accelerating. The truck is not accelerating. If it's going at a constant velocity, it's not changing its velocity, and that's what acceleration does. It slows down or speeds up your velocity. Anyway, so there is zero acceleration. There is a constant velocity. And so if this car keeps accelerating, it will catch up to the truck. The question is, how long does it take? So we build a little equation. Let's see. Here we got the car. We got the car's acceleration. It's 10. If I integrate, I get the velocity equation. So how do you integrate a 10? I'm integrating a 10. Antiderivative, integrating a 10. The answer is, with respect to t, 10t. Oh yeah, plus c. The plus c is the initial velocity of the car, which was stopped, remember? So its initial velocity was 0. Now I want the position of the car, s, the position of the car, which means I integrate again. I'm integrating 10t. You know how to integrate. T squared divided by 2, 5t squared. Plus another c, which is the initial position of the car. I guess let's just call this initial position 0, sitting here at this red light. So that's 0. So I've got the position equation of the car. What about the truck? The truck had 0 acceleration. Remember, we're not going to start with acceleration. We're going to start with velocity of 30, and we're going to integrate to get the position equation of the truck. To integrate with respect to t, you get a 30t plus his initial position, plus c. But his initial position, again, was this place where this problem started here, where at the red light, at the green light, where we're calling 0. So that's 0. Wow. So I have the position of the car, I have the position of the truck. The question was, when do they catch up? When does the car catch up to the truck? So I think I'll set them equal to each other. 5t squared equals 30t. The way you technically should solve this is subtract the 30t over, get it equal to 0, factor out a 5t. This is beautiful. T minus 6, is that what that is? I set this equal to 0. When t is 0, they had the same position. That was true. That was at the green light, red light. That was at t equals 0. That's not the time I wanted. They catch up to each other when t is 6. When you set this equal to 0, t is 6 seconds. So the car catches up to the truck in 6 seconds. By the way, the car might be going too fast. Let's see. By the time it does that, let's see how fast is the car going. Do we have a velocity formula for the car? Oh, here it is. So the car is going, right, at that moment, the car is going 60 feet per second. And it zooms right by the truck at that moment, t equals 6. Let's see, do we know, I wonder what the position is. How far away from the red light was this? When t is 6, do we have a position for the truck? Oh yeah, there's position. Remember, position, velocity. That would be 180 feet. 180 feet. What if we plugged it in here for the position of the car? It should be the same position, right? 6 squared is 36 times 5, that's 180. Right, so the position for both of them is 180 feet. This is the velocity of the car. So it depends on the question. That's how long it takes, and here's some other added information. So I like these problems. There's some better ones. I can make up a good one. Look for some assignments. We might be ready to move into 5.2, where this section, this topic of antiderivative sort of switches gears. It's a beautiful topic in 5.2, 5.3, 5.4. I could kind of lump that together and move on ahead. All right, keep doing homework.